Hello everyone, my name is Abhishek Shendre. I am Principal Software Engineer working for D2S at Pixel Level Dose Correction Software. And today I'm going to talk about making curves manufacturable with OP computing, a sampling theory-based approach. I'm the lead author on this paper, and my colleagues Nagesh and Aki are my co-authors. So let's get started. A full chip curvilinear masks are better for wafer quality. A lot of studies have been done in the past to explain how curvilinear masks are actually better. And for example, the paper on the left is a study done by Ryan Pierman, who is working for Intel at the moment. And he does a comparison of conventional OPC with curvilinear OPC. And what he found is interesting. Curvilinear OPC tends to have less EPE variance. As you can see from the chart, the spread of the curvilinear OPC is actually thinner compared to conventional OPC. So what this explains is that wafer quality will be better because if the masks are better, the wafer quality is better. And if there's less variance, then of course the wafer also will have less variance. And a mask that is fully curvilinear for the entire chip, like for example, something created by TrueMask IoT, as you can see the mask on the right side of the screen, right? So such masks will overall lead to a better wafer quality. But can we produce any curve? Consider this test case where you have the light blue colors representing the contours that you actually wanted to print, and it is overlaid with a SEM image. As you can see, some regions, some of the curves are really manufacturable. There is no issue manufacturing. But maybe there are some other places where it is too sharp. And because the curve is too sharp, the process doesn't allow it to be manufacturable. And in these cases, the smaller regions are really towards the edge of the leading edge manufacturability. So even a shape, even the same shape, right, may not print for a different process. Here I'm comparing three different shapes and three different processes. So let's say you have a 25 nanometer diameter circle, and we have three different processes modeled with a single Gaussian blur, right? So the left one refers to a 15 nanometer Gaussian blur. The middle one refers to a 12.5 nanometer Gaussian blur, and the right one refers to a 10 nanometer Gaussian blur. And in all these three cases, you can see the left one will not print, the middle one, it may print, and the right one, it will actually print with a good quality. Now, the middle one and the right one, what's the difference? You can see the colors over here. The green color represents a good dose margin, and a red color represents a bad dose margin. So you can see the middle one, it was able to print the circle actually smaller than the target, but also while printing the circle, it was doing it with a bad dose margin. While on the right side, the circle was printed larger, closer to the target, and it was with a good dose margin. So if we extend this experiment through different curves, different ovals of different widths and heights, and try to understand what happens, you can see that as your aspect ratio changes, the curvature is becoming sharper and sharper. And the sharper the curvature, the more difficult it is to manufacture. And in general, improving the process blur will help manufacture these sharp curvatures. So as you move to the right, you can see the curves are better manufactured. You have better dose margin, although even on the right, you can see the dose margins for the sharper regions are getting towards yellow, which means it's not bad, but not extremely good as well. But for the middle and the left process, you can see that for tighter curvatures, the dose margins are not good. So physical process blur governs the smallest reliably manufacturable shapes. And here, the smallest also refers to the smallest curvature. So is there anything else that can affect manufacturability? Well, remember, mass shapes are essentially sampled into pixels. So you have an input design, you rasterize it, and you then write it with the multi-beam mask writers. These are for all the leading edge masks. You have to write it with a multi-beam mask writer. So it has to go through rasterization process because multi-beam mask writers only writes with pixels. And there is no accurate polygon in the pixel domain, right? The exact location of a vertex is not really used in computing the wafer quality or for mask inspection or even to write the mask. So whether you write the blue curve or the red overlaid curve over here, they will rasterize exactly the same. So inherently, rasterization acts like a low-pass filter. And the red and the blue curve, you can consider them to be equivalent because both of them rasterize to the same pixel values. So what you get on the mask is going to be exactly the same thing. So pixel dose equivalence is sufficient. Now, whether you use polygons or the new multigon method to represent the curve, it doesn't matter as long as it's the same pixels that is what you're getting after rasterization process. So you may choose to sample the curve at a very high frequency, like every 1 nanometer. But if the multi-beam mask writer has larger pixels, you're basically just wasting the compute capability. So computing beyond multi-beam mask writer's capability is going to be wasteful. And pixel level dose correction software takes this into account. It works in pixels. So it knows the multi-beam mask writer's pixel size, and it uses that pixel size for its own correction. The pixel level dose correction software can actually improve your LCDU by more than 20%, GCDU by more than 20%. It can also improve your linearity by more than 40%. And all of this is achieved with zero added turnaround time. You can do entirely curvilinear masks, or you can mix it with Manhattan designs, and it will still be doing everything in zero turnaround time, whether each and every section of the reticle is curvilinear. Now I'll go into the details of how it does it. So this has been proven by various papers from Texan and Micron. You can see on the left side, there's a paper presented by Texan, which actually won a subsequent paper in the same series, won the best poster award in PMJ this year. This one, it actually studies a dot array, and it sees that with PLDC, the LCDU, that is the local critical dimension uniformity, actually improves when you have PLDC on. On the right side, there is a paper by Micron, which also does similar studies on their own patterns. And they also found that LCDU got improved by more than 22%. And it was also noticed that even the linearity got improved. So all the EPE errors were much smaller than not using PLDC. And we had 44% reduction. They also did a study of figuring out whether indeed PLDC is zero turnaround time. So what they did is they did a run with PLDC on and with no PLDC. And what they found is that the overall runtime change was negligible. So this truly demonstrates how entirely curvilinear mask is done in zero added turnaround time when using PLDC. How does PLDC do it? Well, PLDC can modulate dose intensity to improve the dose margin using edge enhancement. What is edge enhancement? It's basically you increase the dose near the edge of the shape. So when you increase the dose near the edge of the shape, and if you try to simulate it, you would find that the dose margin, as you increase the dose, improves because the dose slope improves. And the steeper the slope, the better is the dose margin. And whatever the shape you are trying to print, at threshold, if you find the slope or the simulated slope or the actual slope to be bigger, you will find that it has a better dose margin. A better dose margin actually leads to a better LCDU. PLDC can also modulate the shape width to hit the target accurately. So what it does is it can change the size of the shape, and it actually computes how much to change it based on a model. So there will be a true model, which is a fully calibrated model. And what it tries to do is to come up with a width that, according to this model, will make the correct corrections. And it can do full MPC based on that. So PLDC corrects the beam blur effects of all magnitudes, whether it's PEC range, whether it is the mid range, whether it's the short range. It can correct errors of all blur magnitudes. It can do edge dose enhancement, which actually improves your LCDU and also to some extent GCDU. And it can do variable edge bias, which improves the linearity even further. So together, with all these three options, it's actually doing geometric effects, which are basically corrected using a geometric bias. And it's doing the dose effects, which are corrected by the dose bias. So that's the beauty of PLDC. You get geometric effects corrected by geometric bias and dose effects corrected by dose bias. Now, remember, the physical process blur actually governs the smallest reliably manufacturable shape. Again, I'm showing the slide that I just presented a few slides ago. And this particular experiment was done without PLDC. So let's concentrate on the middle process here. So let's look at the 2.5 nanometer Sigma process blur. And this was without PLDC. But when you use PLDC, you can see how different it is when not using PLDC. So you can see all the dose margins are much better. You can also see that the shapes are actually printing to the actual desired target. In fact, if you compare this for 12.5 nanometer process blur with PLDC, and if you compare this with a 10 nanometer process blur without PLDC, you can see that with PLDC, even for a bad process, it's producing better results compared to a good process. So I'm just considering this a bad process in a comparative basis. So here you can see that PLDC actually helps achieve the quality of a better process. So inline PLDC corrects every pixel on the reticle, and it is customizing this correction for individual local and global context. Well, offline solutions can also do this for a full reticle to consider the global context, but considering global context would be too slow for offline solutions, and it would be too much data to be practical for offline solutions. So inline PLDC is in a unique position to do both local and global context more accurately. Here, the important thing to know is that there are dose-based effects and there are geometry-based effects. The electron scatter and resist blur, these are examples of dose-based effects. The edge bias and resist shrinking, these are examples of geometry-based effects. So the geometric-based effects shouldn't be corrected with a dose-based correction. Correcting one of these effects by the other is going to be incorrect. And I'll show you how that is to an example. So let's consider a case study. Now, let's say there is a chip, and or let's say there is a full mask reticle. And a mask reticle is generally made up of a bunch of chips. Let's look at one of these particular chips. And let's blow up the chip and let's look at one of the regions within the chip. Now, this chip region, let's consider that they have similar loading effects, because loading effects are typically a millimeter scale effect. And within this chip region, we will characterize three areas. One is the green interior area, there is a blue edge area, and there is a yellow corner area. Now, imagine that all these three areas have the same shapes, and there is a SRAF, there is a main feature. Now, let's take a cross section of these shapes. So you have the SRAF and the main feature cross section on the right side. And understanding the dose-based correction will require us to do some dose margin analysis. So this analysis will basically require us to do a full short, mid, and long range effects corrections and simulations. So let's just consider that and let's just see. So for 193i SRAFs, the SRAFs can actually print with good dose margin compared to the main features. So the SRAF's dose margin and the main features dose margin, if you consider the full short range, mid range, and long range effects, the dose margins are very comparable for the particular process that I'm considering in this case. And what this means is whatever kind of dose-based correction you try to do on the SRAFs, they would have a similar effect on the main feature and vice versa. But if you go to high NA SRAFs, well, in this case, you will find that the SRAFs will have a relatively bad dose margin compared to the main feature. Since the dose margins are very different between the SRAFs and the main features, if you try to do any dose-based correction, that will have some additional effects. So let's just consider the same three areas, right? Here, the green curve represents the interior, the blue curve represents the edge, and the yellow curve represents the corner. And if you look at the dose margins, you can see that it is very different for all these three regions and even for the SRAFs and the main features. So both features have different dose margins for all these three regions, so all 6 cases. Now, if you try to consider a loading effect, let's say of 2.1 nanometer in all these regions, then you would have to do a 2.1 nanometer bias. So in order to come up with that bias, let's say we do a 5% dose increase. Now, what happens is we tried to do a 2.1 nanometer bias by a 5% dose increase. We only achieved it in one region. The rest of the regions could not get the 2.1 nanometer bias. In fact, the bias was ranging from 1.4 nanometer to 3 nanometer. Now, this is because all these 6 cases have different dose margins. So if you just try to do a dose increase and expect the same bias, well, that's not going to happen because of the dose margin differences. But if you do PLDC, because it achieves the geometric bias for all these locations, the SRAFs and the main features get corrected by a proper amount, and all of them get the 2.1 nanometer bias. This can be seen here. So comparing the two charts, we can see that without PLDC, the bias depends on the local dose margin, while with PLDC, the achieved bias is consistent everywhere. This is because it's doing geometric bias in pixel domain. And Micron shows a 24% better GCDU when using PLDC. Here again, because the geometric effects are corrected inline by geometric bias in pixel domain, it has the better dose margin based correction, and it has better GCDU. So here on the right, we can see a heat map which compares the at full chip level, what is the difference in the global CDU. And you can see that there is more variance on the heat map without PLDC compared to with PLDC. And that's the reason why PLDC was able to improve the GCDU by 24%. So PLDC with GPU accelerated OP computing enables manufacturing of curvy shapes. It improves LCDU and GCDU by more than 20%. It can do full linearity correction, including variable bias, and improves the linearity by more than 40%. It can do Manhattan or entirely curvilinear reticles with zero added turnaround. Every CD variation on mask is a CD variation on wafer. PLDC improves the mask CDU and thereby the wafer CDU. Thank you very much for listening to me on this talk. Thank you.